Okay, welcome back to the last video in the series of estimating a population mean. Okay, remember the standard error of the mean? Well, I've just discovered that your book does not use that notation and simply always substitutes s over square root of n. So I will continue to do the same. And so in this case, it is equal to 8 divided by the square root of 20, which equals 1.789. Now that we have the standard error of the mean, we can fill out the rest of the graph, which is a nice exercise to help understand things, but not strictly necessary to solve the problem. Because once we have the standard error of the mean and the t-value, we can now compute the margin of error. So E will equal the t-value times the standard error of the mean. In this case, that would be 2.539 times 1.789. Now you may do it that way, however, there may be some rounding error if you choose to evaluate things too quickly. It is often better to substitute directly into the standard error of the mean at this point. So for this problem, we wind up with 4.5419, or approximately 4.54. Going to the hundredths place is usually all that's necessary to communicate what we need to. And now to summarize things. We were looking for a 98% confidence interval. So 98% confidence is where we began. And these were the values we were originally given. And the values we've calculated so far are listed there: the standard error of the mean, the t-value, and the margin of error. Only these three go into our final answer. We can say we are 98% confident that the mean of the population equals 50 plus or minus 4.54. So that's 50, and plus 4.54 gives us 54.54, while minus 4.54 gives us 45.46. So we could say we are 90% confident that the mean of the population is between 45.46 and 54.54. So to summarize constructing a confidence interval. You can do this if and only if IFF, your sample observations are random, your sample size is small relative to the population, so the population is greater than or equal to 20 times the sample size, and the data come from a population that is normally distributed, or your sample size is large, greater than 30. How do you know if a distribution is normal or not? Well, you do some analysis, as you've learned to do. Make probability plots or analyze a box plot. So let's look at an example where we have a large sample size, even though we don't know how the population is distributed. So let's construct a 90% confidence interval for the mean of the population when we have taken a sample of size 40 from that population and calculated that, oh, that's in the wrong place, the sample mean is 35.1, and the sample standard deviation is 8.7. Let's take care of that confidence interval first. We will change 90% to 0.90, its decimal form. We will find alpha. Alpha equals 1 minus 0.90, or 0.10. And alpha divided by 2 equals 0.05. And that means that we would have 90% of the data between those two values. We need one more thing before we can refer to the t-table, and that is the degrees of freedom. Since the sample size is 40, the degrees of freedom, or the degree of freedom, is 39. So we go down the side to 39, and we go across to the column. That corresponds to 0.05, and we get 1.685 That is the t-value for the area 0.05. So now our margin of error is equal to the t-value, 1.685, times the standard deviation of our sample, divided by the square root of the number in our sample. And when we perform that calculation, we get a margin of error of 2.3178, or 2.32. This seems to be a rather small margin of error. There are two reasons for that. The standard deviation of the sample was very small, but also our sample size was large. So we were dividing by something larger than we were previously. And when we remember that the population mean is estimated to be equal to the sample mean, we can now state our confidence interval. We are 90% confident that the mean of the population is, I forgot to write it down here, 35.1. 35.1 plus or minus 2.32. And this is a convention we will follow. To whatever decimal place the mean is expressed, in this case, one place to the right of the decimal, we will go one place further. So in this case, 2 places to the decimal, or to the hundredths place. And this is our confidence, and this is our interval. We have expressed a confidence interval. That's enough video work. Tomorrow we can talk about this during our Collaborate session. See you then.